Let's prove 0.9 recurring is equal to 1. Okay, so the first thing that we're going to do is multiply both sides with 10 so that the decimal place shifts. Right. So we have two equations now. We could use the second equation in method 2. All right, so let's start with substitution. 10x is equal to 9 plus x. X is just 0.9 recurring. And, we could just remove x from both sides, subtracting x on both sides, which will give us 9. X is equal to 9. Divide both sides by 9, and there it is. X is equal to 1. Same as substitution, just you're going to be subtracting equation 1 with equation 2 over here, which will still give out 9x is equal to 9. Divide both sides by 9 again, and the 8x is equal to 1. Two completely different methods, but they give and yield the same answer. Let's, look at a circle this time, because it's just numbers. Okay, now we're going to use an actual geometric proof, a circle. Let's slice the circle up into 3 halves, slicing it up into 3 halves. Each half is 1 by 3. When we add all these together, 3 over 3 simplifies to exactly 1. Alright, same circle, redrawn again. We're going to see that 1/3 of a circle, which is one part of this 3 divisions, is equal to 0.3 recurring. When we add these 0.3 recurrings together, which is 1 by 3 plus 1 by 3 plus 1 by 3, we get 0.9 recurring. Right? Because each half represents 0.3 recurring. We get 1 when we add all these together, which is, 3 by 3, which simplifies to 1. This is another way to show you guys that 3 by 3, which is equal to 1, is equal to 0.9 recurring. Let us step aside from 0.9 recurring for a while because we have just proven it that it is equal to 1. And let's look at something different. We know that repeated addition is multiplication. Add 3 twice, you get 6. Add 3 thrice, you get 9. 4 times 12, which is exactly what 3 times 4 means. 4 threes stacked. Let's look at repeated multiplication, which is powers on exponentiation. Same trick, just multiplication instead of addition. 3 squared is 3 times 3. 3 cubed is 3 times 3 times 3. And 3 to the power of 4 is 4 3's multiplied together, and that's 81. Let's look at some special cases for exponents, because after this, we're going to be looking at something that's even bigger than exponents. As you can see, negative flips into a fraction, 0 collapses into 1, and a fractional exponent is a root. 1 by 2 power 9, 9 power 1 by 2, which is equal to under root of 9. Let's see, why do these cases work like this? Like, why is 5 to the power of 0, 1? Let's take. Let's try to find the pattern using the fifth powers. So 5 to the power of 4 to 5 to the power of minus 2. We see 5 to the power of 0 is equal to 1 because everything is divided by 1. Same rule every single step. 5 to the power of 0 is 1 because dividing by 5 itself always yields 1, and negative exponents keep dividing that 1, landing us in fractions. Let's prove it using an exponent rule. The division rule, a to the n over a to the n equals a to the m minus n. Let's take 5 cubed over 5 cubed. That is 1 because anything over itself is 1, cancels out. By the rule, 5 to the 3 minus 3, which is equal to 5 to 0, which is also equal to 1. This proves that 5 to the 0 is 1. Let's do 5 to the 1 over 5 cubed. That's 5 over 125 or 1/25th. By the rule, that's 5 to the 1 minus 3. So 5 to the negative 2 power. So 5 to the negative 2 is 1 over 25th. It just fell out of a rule we already tested. It divides by 5 2 times, which gives us 1 over 25. Fractional exponents are, roots and squares that just cancel out. Try 9 to the 1/2 squared. The exponents multiply 1/2 times 2, leaving just 9 to the 1, which is 9. So 9 to the 1/2 is the number that squared gives 9. It's exactly the definition of a square root. When we square it, the root cancels out. To generalize it, a to the 1 over n is the nth root of a. We use this simple formula, and here 16 to the 1/4 is the fourth root of 16, which is 2. And for any fraction, m over n, root it, then raise it to the power. This could be used. Decimal exponents and irrational exponents need special formulas like the Lambert function and solve them properly, because these generally don't follow like natural numbers, and each closed rational exponent locks the value tighter into the limit that nails it down to 2 to the pi exactly. Decimals are just fractions, but the numerator is above 1. And we see the full picture here, all of the 5 cases laid down, 4 cases. Repeated exponentiation, it's called as tetration. Tetration is a power tower, exponents stacked on exponents. Write it with a left superscript 4-3. You can see the 4 is on the left side instead of the right side, which is 3 tetrated to 4, a tower of 4 threes. That is 3 to the 3 to the 3 to the 3. Here's the catch. Power towers evaluate from top to bottom. We start at the top. 3 cubed is 27. We substitute that back in. Now the tower reads 3 to the 3 to the 27. Evaluating 3 to the 27, which gives us 7.6 trillion. Now we substitute that number and the whole tower collapses. 3 raised to 7.6 trillion. That is big. For comparison, 3 to the power of 4 is just 81, 2 digits. We are seeing this chart here in bars, and the bar doesn't even fit in the chart. We just left it out. It doesn't even fit on the screw. If we keep climbing, pentation and hexation. Pentation is repeated tetration and hexation is repeated pentation. These arrows, each extra arrow stacks one more level of repetition on top of the last. So like after hexation, another arrow adds septation, octation. It depends on the arrows and where are we seeing what these arrows mean in a setup. 3 times 4, repeated addition. 3 to the 4 is multiplication. 4 to the 3, repeated exponentiation, tetration, and hexation. All of these are ideas which are built on top of each other. So let's understand what these arrows. These are nuts up arrow notation, right? Every extra arrow means take the previous operation and repeat it. A single arrow denotes a to the power of t, which is just basic exponentiation. 2 arrows are tetration, 3 are pentation, and 4 are hexation. Here's the rule under every arrow. The base case, 1 arrow is just exponentiation, and the recursive step n, arrows on b, equals. Drop 1 arrow, then apply that lower operation to itself b times. Read it left to right. Drop 1 arrow but apply it b times instead of once. Let's actually run this machine. 3 triple arrow 3. By that rule, 3 double arrow applied to 3 double arrow. And 3 double arrow 3, that's tetration, which is 3 to the power of over 7.6 trillion. That's tetration, same thing. Let's look at factorials, which are, also big numbers which you are working with. The factorials are numbers which multiply n for every positive integer below it. 3 factorial is 6, 5 factorial is 120, 9 factorial is 300,000 approximately. 0 factorial is defined to be 1 and negative factorials are undefined for now. The double factorial is not applying factorial twice. That will be n factorial. Instead, it multiplies every integer up to n that shares n parity. Parity means even or odd. 3 double factorial is just 3 times 1 because odd numbers below 3 are 1. 9 double factorial skips every other even number because it's odd. So 9, 7, 5, 3, 1, giving 945. Superfactorial is the product of every factorial from 1 factorial up to n factorial. 9 superfactorial multiplies 9 factorial times 8 factorial all the way down, landing around 1.86 tilli. Primorials are numbers which multiply together every prime number or less than equal to n. The primes up to 9 are 2, 3, 5, 7. So 9 primorial is 7 times 5 times 3 times 2. The prime numbers which are and below the given n number. So that's primordial. And then hyperfactorials are numbers which take integers from k from 1 to n and raise each one to its own power. Like hyperfactorial 5 is 5 to the power of 5 times 4 to the power of 4 times 3 to the power of 3 times 2 to the power of 3 times 1 to the power of 1. H of 9 keeps that pattern going all the way up. The result is really large, like even larger than 3 to the power of 7 sextillion that we saw, trillion that we saw. And these last thing is the gamma function and full derivation. 0.5 factorial is gamma of 1/2 plus 1. The gamma 1/2 as its integral, substituting t equals x squared, and the integral turns into twice the integral of e to the negative x squared. Call that integral I, then I squared becomes the double integral with the whole form. Switching polar coordinates, it collapses into a clean r and theta integral. Solving that, I squared exactly equals pi. If you guys have made it to the end of this proof, your attention span is really good. You're also one of the very first viewers to this channel. Subscribe and Axiom out.